Okay, so from the programmer point of view, let me ask you the simple question. When you malloc, once you malloc, right, you use the pointer, and you have to worry about any other programs that would invade your space at all. So how can the OS tell? So what would happen? So the first question is, let's say if I have a program that invade your address space, which means that someone tried to read a location that doesn't belong to yourself, what would happen? Any old friends from the assignment 3 that you hate? Seg fault. It's called segmentation fault for a reason. Back in the day when we have x86 processor, the address space, sometimes we would divide it into segments for different purposes. Seg fault means that your access going to the wrong segment, right? And what happened after the seg fault? So what happened when you have a seg fault? Except for you were like going back to your program and trying to figure out what's wrong with your program. It crashed your program, right? So from the programmer point of view, if you have a legit program, do you have to worry about any other program that tries to read your data? In the ideal case, no. Except someone hacked your computer, all right? Obviously, that's the problem. But from the programmer point of view, I should see the abstraction of the memory, right? Should be unlimited. I can always keep malloc until, well, to be honest, Stack Overflow, right? But I want to have unlimited memory. Let's say I run 1,000 different programs at the same time in the computer, right? It'll be slow, but parts of your data will be in your hard drive, right? But it looks unlimited because I don't stop running at, say, 16 gigabytes. I keep going, right? It should be contiguous. For example, you have an array that is 10,000 entry long. There should not be any random gap in the middle. When you use the pointer, when you pointer +1, pointer +2, pointer +3, you should not have to worry about, hey, there's a gap between pointer +3 and pointer +4 that is like 70 bytes long because it's owned by someone else. It should be contiguous. When you malloc, you should get a whole block of data that's next to each other. All right. Think about, let's say I have two programs that running together for a long time, and I have malloc. I have free malloc, free malloc, free malloc, free. What's the chance that you don't have enough room to fit your data when you malloc again? It's possible, right? You can have fragments of the free memory that each fragment is not big enough for your data. All right, so keep that idea in mind. The thing is, you never run into that problem. You can always malloc. And when it's actually out of memory for your stack, you just say, hey, stack overflow malloc return null. I don't have the pointer back. Somehow the OS and the hardware manage that task. Why is that good? Yeah, make the whole like programming experience flow quite well, right? You don't have to worry about this low level thing. And somehow the OS should ideally manage it for me. All right. That's what you get from virtual memory. So inside the hardware, when you buy your DRAM or your main memory, right? These are physical things that you buy, you plug into your computer. So the thing is, somehow there has to be a relationship between the pointer that you're using and where your data is in the physical memory. I'll call this the physical memory now, which is your actual data, the location of your actual data inside DRAM. We call these things physical memory. And the pointer that you use, that becomes the virtual memory. And the concept of virtual memory is, can I have a mapping between a virtual address, which point to the virtual memory, some location in my virtual memory, into the physical address, which is some location in my DRAM. That's it. I just need that map. All right. Now, the issue that we're going to talk about for the entirety of today is how to make sure that map is easy to manage, right? And doesn't cost too much in terms of performance. Okay. So what exactly is virtual memory? Basically, when you get a location in DRAM, we actually got the physical address, the actual real location. Think of it as your home address. Then you can put a nickname on your home address, right? The actual address will be like with the house number, the street name, with the district, with the city name, with the postal code, right? That's the physical address. Then I can give the nickname to that location. That's my home. That's MUIC. That's Chulalongkorn University. That's is like, I don't know, like some mall around here, Central, Salaya, for example, right? Those are the nicknames. You set the nickname, everyone know where that location is. Think of the nickname for the location is that's virtual memory, virtual address. It's in the virtual world that you can map, you can redefine the name, and it will point to the correct physical location of where things are located. All right. Any questions so far about the high level? Okay. So this is the beauty. Each process that you run, basically the program that you run, they have their one single view of their virtual address. Think of it as each program has their own like metaverse, like their own universe of these are my address, and then the OS will make sure no one invade your universe. They have the physical location somewhere, and that's my address that I just have to look into and manage and deal with my data. I don't have to worry about any other universe at all, right? We call this virtual address, and the space for each program, sometimes we call this address space, which is owned by each process. Yes. The what? The what address?
Just use the real address.
The real address. Okay, great question. That's a great question. The thing is, for the real address, right? Let's say you use the real address, and let's say you malloc, and you ended up fill up this whole physical location, and you have to remap some addresses to your hard drive because your address is full. At that point, you don't even have the real address because it's in the hard drive. So that's the first benefit. Second benefit is if you use the real address, you still need some mechanism to prevent people from attacking my address, reading into my address. So with that, you need some way to manage them anyway. The third benefit is, let's say you do malloc like this, right? Occupy. Now, let's say I have a red program finished running some of my parts of my program. I free up this, right? That's a program number one, and that's your DRAM. The second program comes in, the blue program, say, hey, I want to use the memory too, but I need this big, something this size, which fits 2 boxes. But I don't have enough space for 2 boxes, right? And I want to make sure I have enough space for my array. My array called A. I have A0 start from here and A say 100,000 ends there. It means that my address, if I use the physical address, it spans 2 locations. Which, from the programmer point of view, it means that A of 50,000 and A of 49,999 are not next to each other, right? So in that case, let's say you loop around, use pointer arithmetic, and you add A 499999, you increment to A 50,000, and you're basically in the red region. It's not your address. And that's one of the biggest benefits of virtual memory, because in that case, you just need to make sure the mapping that the first half is there, the second half is in the other location. As long as your program goes from A0 to A10, 100,000, it knows exactly where's A of 49999, which is basically right here, and then A of 50,000 will be right here. But from the programmer point of view, those two things looks like they're next to each other.
Isn't it a lot slower?
Isn't that a lot in terms of what?
So, or more expensive than?
Yes, yes. So the key here is does provide what we call sometimes programmability benefit. Your life as a programmer is easier, but it comes at a performance cost, right? Which is what we're gonna go through today. It does slow down your program, and it does come with overhead because someone has to manage it, which is basically the OS. The OS has to actually have a code to manage this whole thing. So for this, both the computer and the hardware would work together. In the hardware, there's this thing called memory management unit that perform the mapping, that perform the translation of the mapping. I have this virtual address MMU will allow you to access the physical location automatically by the hardware. And the OS just have to like basically perform the mapping. Say, hey, this thing goes here, this thing goes here, this thing goes here. Now the hardware would be informed about the location and go through those addresses. So the first benefit, you have this virtual space for each application. Simplify the programming effort. You don't have to worry about anyone else or anyone using some part in the middle of your array. Second benefit, memory protection. This gives you the segfault that you hopefully love by now. It's a good thing because if you try to read some random location that you did not own and you overwrite some of that number, and let's say that turns into your Linux or Windows data, it could crash your computer, the whole thing, not just your program that you're running, right? So you get memory protection. You know who is trying to access what, and is that a legal access, right? Now, the third benefit is, let's say you have limited memory, like on your phone, right? Sometimes you have to use the hard drive or the storage SSD to cache, not to cache, to store your memory data. In that case, it allows you to do the mapping between the virtual address instead of going to DRAM. Now it say, hey, it's not in DRAM. The OS would kick in, it would basically know, okay, it might be in this location in your SSD, and it would look through that location for your data. This allows you to expand the size of your memory into your SSD or hard drive. And if you use Linux and macOS, this space is called the swap space. So if you have swap space allocated and are being used right now, just be aware those are hard drives, not your memory. But if they're being used for your addresses in the program, okay? Sometimes we actively use them. For example, how many people have an app on a phone that you opened like 1 month ago and you never open it again, but it's still like in the background? Yeah, why do you have to put those in the memory? It doesn't make sense, right? So you can put that in the swap or even kill that program. So cold, something we call this a cold data. Cold data means that the data that you know that you're not going to use it again for a long time, based on the frequency of how many times you access this piece of addresses, you put them in the disk. That's a valid strategy to free up the room in your DRAM, right? Now, to actually understand virtual memory, let me first define some definition. The first thing is what we call a page, all right? Similar to a cache block, it's a unit of space. Now, the mapping, so I basically motivate virtual memory by when you have a virtual address 1 will be mapped to a physical address 1. Virtual address 2 will be mapped to physical address 2, right? Each virtual address will be mapped to some physical address. The problem is if I manage it in the address level, which basically means that every single byte has their physical mapping that can go anywhere. That will be really hard to manage because how many bytes you have in DRAM? It's a lot, right? To simplify the management, you will basically have this. I have the virtual page that map to a physical page. So anything that go into that page will go into that particular physical page, and there this one contiguous block that are next to each other. So the address that go into the first location here will be mapped to this location here. The address that go into this corner here will be mapped to the address that go into the corner here. So that way, you don't have to do one-to-one mapping for every single byte. You just have to do the mapping between one virtual page into another virtual page. All right. Anything inside the page will have the same organization as the physical address. Virtual address inside the page, physical address inside the page have the same ordering, same order, same organization.
Are there chances for outside programs to access these pages?
Great question. Theoretically, no, but we have to have something built on top of it so that I can make sure that if I have my virtual page, no one else can access it. We call that permission bit. There are ways to add the permission bit to the information while you're trying to figure out if this is where's my physical address. It would have the permission bit, and you can check the permission bit of that page. If they match, it means that's yours. You can access. It's fine. If it doesn't match, that's not yours. Sec fault. You die. All right, your process died. I kill your process.
Is there chance for the permission bits to get activated?
Being hacked, yes. Otherwise, no. If you're being attacked by some security threats means that a possible attacking location that right now your system have, no one attacked it yet. So if the attacker comes in and know, oh, you have this threat open, I attack that threat, there's a possibility that you can go into someone else's virtual pages. All right, so again, the page is a much bigger range of data. For example, your computer would use a 4 kilobyte page. There are also proposal, and some machine also use a bigger page size, like 16 or 64. For example, a GPU, your graphic processor, will have a bigger size because it actually works well in that size. Now, the size depends on how you use your DRAM. What program are being run on? Your CPU, typically Linux, managed at 4 kilobyte page size. So each page is exactly 4 kilobytes. Again, this can be much bigger. For example, yeah. Huh?
Can you manually adjust the size of?
Yes. Linux, for example, has this thing called THP. THP is what we call huge page support, where instead of using 4 kilobyte page, right, you combine 512 of that and make a 2 megabyte page out of it. Right. So here, let's say this is your virtual address, and this is your DRAM, right? You have virtual page 1 here, virtual page 2 here, virtual page 3 here, virtual page 4 here, right? Now imagine these are consecutive addresses, pointers that you use in your C program. They are next to each other. The way they are actually being mapped in DRAM can be in any order, in any way the mapping can be, right? So in this case, for example, virtual page 1 might be here, physical page 1. Virtual page 2 might be all the way down here, physical page 2. Virtual page 3 might, by chance, here, physical page 3. Virtual page 4 might be somewhere here, physical page 4, right? This allows you to basically exploit the tiny spaces inside your DRAM so that if you want to have a bunch of data, for example, you malloc, but you need 8 gigabytes, 8 kilobytes, my bad. It means you need 2 pages, right? Your array will get 2 pages of data, virtual page 1 and virtual page 2, for example, in this case, right? From your pointer point of view, it's next to each other. The virtual page 1 and virtual page 2 are literally next to each other. Yes.
Can you break down works?
Like let's say you have a smaller physical page, right? That that demands some hardware changes. So by default, your CPU doesn't have that, but that can be a good idea for certain hardware design. All right. So yes,
What's the benefit?
for example, right, if let's say your machine only support big page size, like let's say 128 kilobytes, but you detect that say your program used just a bunch of like 10 kilobyte pages, like data chunks, right? It might benefit to break it down to sort of squeeze into like the room in the middle to get a better use of your data. Because I mean, you malloc for 10 kilobytes, right? You actually got the entire 128 kilobytes. So you are actually not using quite a lot of your data at the moment.
Just wasting the.
Yes, and then one thing you can address that is through, for example, rewrite how malloc works. So malloc is a program. It's some function that someone writes for you, right? So you can rewrite it in a way that, let's say you malloc for 10 kilobytes. It try to attach multiple 10 kilobyte malloc together so that it becomes like a much bigger block of consecutive addresses. So that's actually what something malloc try to do all the time as well. The space that are gone because of this inefficiency, we call this fragmentation. And fragmentation is when you have fragmented memory, where it's like, I have this room for like 2 kilobytes, I cannot use it. I have this room for like 15 kilobytes, I cannot use it. Fragmentation is a big problem for the system with large page, like 2 megabyte page. But again, there are many big data applications that have to deal with large range of data, which can potentially benefit from huge page, right? Because why do you have to do this 4K mapping all the time? It does have overhead with smaller page, incur higher overhead, so bigger page, lower overhead in terms of performance, but you have a lot of fragmentation. So it has to strike the balance between the two. And the physical page is mapped somewhere in DRAM, essentially. The program for any address you see so far, that's the virtual address. You never seen the physical address, which is the beauty of programming, because if you have to manage the physical address, it can be really annoying. Imagine that's your DRAM and that's your physical address, right? You have an array that span virtual page 1 and virtual page 2, at different locations. Not easy to tell where they are, right? Then also virtual address maps to the physical address in DRAM, and they belong to a physical page. So the way I would like you to think about it is, a virtual address will be in some virtual page, and that virtual page will be somewhere in the physical page inside DRAM. And that physical page, there are ways that you can recover the real physical address afterward. All right. Now, how do we do it? Now, the question might be, let's go lower level. How do we do this? We exploit this technique called indirection, which is actually used a lot in computer science. Indirection means that I treat things like a pointer. And how many people here like see in like games like Treasure Hunter where you have a clue and you go to the first location. The first location has a clue for the next location. Then you keep going until you at the end where you find the treasure. The first clue is your virtual address. Your treasure is the physical address, the data that you're trying to ask. Indirection means that clue. I don't give the whole thing. I don't give the direct path to the end location. I give you indirection. So if I have a virtual page that maps to a physical page, right? And let's say your system right now you have 1,000 tabs on Chrome, which by the way should crash your computer, right? But at that point, you're gonna have a lot of virtual pages because all those tabs would demand more memory, right? And you're gonna have way more virtual pages than what you have in DRAM, the physical page that you have in DRAM. It means that there have to be some mapping, right? The first thing is, how can you tell where is that location, right? So that's my first problem. The first problem is I got a virtual page. How do I get my physical page? We use indirection. Think of it as I have a giant table, that store the key would be your virtual page. The value that's tagged with the key is the physical page. So if you search the table and you see your virtual page number, it will give you the physical page number, which tell you the location of the physical page. We call this technique indirection. The table becomes the clue in your really close. You can use hash map to implement, right? But in reality, you don't really use hash map. Like we use a structure called a page table structure, page table structure in order to perform this mapping. The problem with hash map, for example, is that you can, by some unlucky chances, after you have a key and you hash it, it go to the same location, which means you have to search through a bunch of things in there. See, is that yours? 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 All right. Still, there are proposals that looks into can we use a hash map instead of page table structure, right? These are just implementation. How do I get what I want? So the thing is, I have a table that can store two possible things. I have a clue, I have a virtual address. I look at the clue, I got the physical page. That's the first possibility. The second possibility, I have a virtual address, I look at the clue, I get the second clue. I get where the second clue is. So I use the virtual address to get the second clue. I go there, I use my virtual address again, look at the second clue, it would either tell me the third clue or your physical page. Think of it that way. Think of it as a treasure hunting game. All right. And we use the table to store the information. The table would take your virtual address. It would tell where in the table you have to search. And over there, you will see the location of the next table or the location of your physical page. Again, you have virtual address going in to my table. The virtual address would tell you what row in the table you have to look at. Inside that row, it would either give the clue on where's the next table or the physical page. Where's the physical page? All right, with me so far. Now, with me so far with the abstract design.
What would you do? Better just to go directly to the
That's great. That's a great question. So let's imagine you have 4 kilobyte page size and your computer is 16 gigabytes in size for the DRAM. How big is that table? Fairly big, right? So one thing that the system do is you would have multiple levels of this table. Your 64-bit processor, for example, has 4 levels. So you have table level 1, table level 2, table level 3, table level 4 before you go to the physical page. But the same logic applies. It's just how many steps that we have to do.
How long will it take for each the process to go?
Great question. That's the next step. How do we make it faster? Because where's that table actually? Let me ask you this question. Where's that table? Great answer. One thing we can do is put them in the cache. But can we fit everything in the cache? No. So similar to the normal data that you have, the table is actually in DRAM, but you can cache them. So you can cache the location. Let's say you have this virtual address, you cache the shortcut all the way to the physical page inside the cache. But the actual table is in DRAM. So let's say I have 4 level table, right? Each level is I go to DRAM once. How many DRAM access until I can get to my data? 4 tables and 1 more data access, right? Which is basically 5 DRAM accesses. Not nice, right? So that's a big overhead. So we'll talk about how to get rid of it. Okay. Or not getting rid of it, but try to not do that a lot. Okay. And basically how to do it, your answer, caching. Because cache is next to the CPU. We can have a separate cache for these guys. All right.
Can virtual memory point to another virtual address another, like double pointer, double pointer.
That's when you have a virtual machine. Virtual machine is basically you run a different OS inside the host OS, right?
I meant like in the C program,
No.
like double pointer, double pointer.
Oh, so when double pointer is like a virtual address that still, when you dereference everything, it points to the physical location.
So if you dereference it once, where does it point to?
So if you dereference it once, you go through the process once. If you dereference it twice, it means that you go through the process once, you get the value. That's like another pointer, so that's like 2 times. So yeah, it does happen. I thought you meant like, can I have a virtual address where once I go down all the way, that's another virtual address in a different system. So that's virtual machine.
Let's do it once for me.
Huh?
Let's do it once for me. I don't know.
We can draw a diagram of what happened next week. All right. So, okay, my bad. So this table will have multiple rows. We call each row the page, table entry. And the table we call page table. Because it's a table that store page location. So we call it page table. The entry in there, page table entry. I hope the name makes sense. All right. And the way it looks is each row here, right, store each entry, and inside them, there are 2 information. Where is the next table? So that's pointer to the next level. So that's where is the next table. Status means permission bit. That would encapsulate, hey, can I access this guy? Is it owned by the kernel? Is it owned by the user application? Is it, what is the address space? Is it read-only? For example, you're trying to write into a read-only data, illegal access, again, checkbox, right? So these are information that you can tag in order to prevent illegal access. Okay?
What if, so you said that for the next level, it's a pointer type thing.
Yes.
Where's that pointer?
So the table is in DRAM, right? Basically, the pointer is stored in DRAM. Huh? Yes. It's like how the node in linked list work, right? But it actually looks more like a tree. So you have a tree at the top level, that's the first table. Each entry spawn another node. So it's like, imagine a tree with, like, say, 1,000 branches that go to the next level table. Then you have 1,000 branches that go to the next level. So the status bit is essentially a permission bit. When you go through the table, you check the permission. If it violates permission, you get an exception. Some exception kill the process. Some exception will warn the programmer something is wrong is going on. This bit can include things like address space ID, who owns this address, read write, read only bits, user versus supervisor bits. The benefit is this is giving you memory protection. It's give you the segfault that you all love by now. Love to hate, I guess. We can use this process to validate our access. Now, hopefully the permission check is clear. All right, it's inside the table. And now when I do the translation, I can check if it's a legit access. The next thing is, how can we actually go through the table, right? So the way we go through the table is we look at your pointer value, which is an address. We call this virtual address. The virtual address has multiple bits, all right? The lowest end, we call this the page offset. Why do we call it this way? Because again, virtual page, right? This is virtual page is mapped to the physical page. What does the word offset mean? It's like,
How many of the person?
yeah, how far are you from some anchor position? right? So the page offset are the bits that tell how many bytes that you have to keep going to find your location of your data from the beginning of the page. So let's say the page offset in a is 0, 0, 0. So that's 4, right? That's 4. It means that you start from here, you go 4 bytes, and you find your data in the virtual page. And the same thing so with the physical page, you go 4 bytes, and you find your data. See how the organization is the same. It's essentially how far you have to go from the beginning of your page into the page to find where is that data. Imagine basically a page as like a page in the book, right? The page offset tells how many characters you have to go from the first letter in that page to find the letters that you want to read from. And virtual page map to physical page. So one page map, it's a one-to-one mapping. So you see that the page offset will start from the same location and go through the same sequence. Any questions so far? Now, the next set of bits are used to look up that table. This works similarly to the set ID. What is the set ID in the caching? It tells what set do you go to, right? So we can use the next set of bits to tell what row are you accessing in that table. So let's go back to your design and say, hey, why don't we have one table and that's it, all right? That's the simplest form. So let's say that's your table. Now my address, again, the lower bit will be the page offset, right? And over here, my table has how many entries? 1024, right? So log2 of 1024 is 10. It means that over here, I will have the next 10 bit. We call this the virtual page number. Why do we call it virtual page number? Because if you look at the virtual address, it will start from virtual page number of 0, then 1, then 2, then 3, then 4, and 5, right? Simple. Simplify the naming and the numbering. Now, the virtual page number will tell you what row you look into here. So let's say your virtual page number is that. What's that in decimal? 8. 8. So it's the first guy is page table entry 0, right? Virtual page number in this case is 8. You have only one level for the table. Because it's only one level, you just go to PTE8. Basically, the 9th row, because it starts from 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's the 9th row in that table. In there, you will find some addresses. That address will point to your physical page. Essentially, that thing, whatever you see in there, will correspond to this location, the beginning of the page. Is the address that point to the beginning of your page. All right. Any questions so far? So one level is easy. One level table, you just extract the top bits after the page offset. That tells you what row do I look in the page table. I extract that to point to the physical page. Now, from this address, right, that points to the physical page, how do I get the real location? I plug in the page offset. Because the base page offset tell me from that location, I go this many, all right? That's it.
The offset is for the actual physical page number.
The offset is from the actual, so over here, right? Let's say this is 4 kilobytes in size, right? This number here, let's say the address here is 0x12, right? So let's say that's the address. Inside the table, you have to store the entire thing. Or can you just store 4 kilobytes is 12 bits? Do I need the last 12 bits? No, because I can get that from page offset. So I can queue off this last 12 bits. I make the table smaller. So in the real system, in the table, you find just this part. Then you plug in the page offset at the end. That's your physical address. Right. With me so far? Okay, cool. So whatever you find in there, depending on the machine specification, which might differ a little bit. So you have to read the machine specification and how they store the page table entry, extract the bits that correspond to the page, physical page number, then you plug in the page offset, you're done. All right. Now, I said I can queue up this 3 bits, right? Which basically means it in reality, you don't really queue up those 3 bits, but you have the 12 bits, my bad, 3 bytes. You basically have those 3 extra bytes for the permission bits. So you use that for the permission check. All right. Oops. I think sorry, I think I have to clean this because that's I think an animation coming. So I'm gonna erase the ink. So you have the page table entry, right? So let's say you have 0, 0, 0, 0, 1, 0, 1, 0. Here, what's that number? 10. All right. So it basically you go somewhere here, which corresponds to PTE entry number 10. Then you got something here, something from here. That thing, we call them the physical page number. Why do we call it physical page number? Because if we sort DRAM from physical page number 0, which is at the beginning of your DRAM, all the way down, that tells me what's the number of that page in DRAM. Then you have the page offset, you plug it in at the end, you're done. That's your physical address. So that whole thing is a physical address. All right. Any questions so far? Again, tricks. All right. You get virtual address, extract the page offset bit. The rest becomes the clue on how to dig up the table. Let's assume one level table, the whole thing becomes what row do I look into? And the entry in the row will tell you where is the physical location of my page. Then you plug in the page offset at the end because that will tell you what bytes am I trying to access from the page.
Okay, so that's a good question.
Yes.
After each page table entry,
Uh-huh.
does it get cleared or no for the previous table?
Let's say
it goes from page 1, like table 1 to table 2. When it's on table 2, does the instruction on table 1 get cleared? So it brings up slot or no?
Oh, okay. So your question is, what if the table gets filled up, right? Yes, there are parts in the OS that would, if it's filled up and you have some program that use it and then the program already finished and terminated, right? It might update the page table. That are actually legit things that do to your page table to update and make sure that you reorganize the memory based on how the program would use the memory. The issue that gets more complicated in that particular scenario is, let's say you have 10 programs running, right? Because you can have malloc and free all the time for all the 10 programs. Then the OS might have to frequently update the page table structure. So it does come at an overhead, so that's a great discussion point. Yeah. All right, any question about the one level table? Okay, so in x86, again, this is like just a tree structure with multiple levels. All of them are in DRAM. All right. Right now, with the 64-bit processor, you have 4 levels. If you have, okay, the root of the tree points to the first level, the first table. The first table tell you the location of the second table, so on and so forth, until you at the end, which give you the physical location of your data. And you use the virtual address and the table to tell where to go next. Again, just as simple as that. I have virtual address. I look at the table. It tells me where to go next. Okay. And each table will store this page table entry that behave like a clue. You take in some value, it spits out the clue. That's your next table. All right. The term page walk is basically the whole process. Starting from virtual address, you perform the page walk in order to go through this page table structure to go to your physical address. All right. Now, if you happen to read older textbook that 32-bit machine, right? So a 32-bit machine, which are CPU back from like 2005, 2004, they will have two level table. 32-bit x86 has two level, 64-bit x86 has four level. So I just need to bring it up in case you read some textbook that include both things, right? It might have the 32-bit and 64-bit version for the x86. And for different architecture, it doesn't have to be always like this, okay? Right now, this is like the default everywhere. Everywhere they use this structure, okay? So 32-bit x86, which is the example that we use, has two levels. The entry store where is the next table with the permission bit as you're seeing down here. Do I have the actual page in memory? Is this like a legit page? Is it read or write, user supervisor, anything that you would need to store in order to figure out, hey, do I need to cache this page? Is it used? Have I modified them and things like that? Is this a global variable shared by multiple people? And then if OS needs extra bit, you can put it there. This is an extra room that you can actually put the bits to manage the page. All right. So let's do this example before we take a quick break. Or should we do a quick break before? Break first or example first? Doesn't matter. Okay, let's go through an example, which we are almost done with this example. All right. Let's assume we have 4 kilobyte page size, which is your normal CPU. You have two levels because it's 32-bit x86 machine. Page offset obviously is locked to a 4K, so that's 12 bits. All right, I pre-compute this for you. Locked to a 4 kilobytes is 12 bits. So the last 12 bits of your virtual address is the page offset. Now I have 32-bit virtual address. Because it's a 32-bit machine, it means my address is 32 bits. I use the last 12 bits for the page offset. I have 20 bits left. All right. Any question about that? 32 minus 12, 20. Okay. I have 20 bits left that I need to use to search two tables. So to simplify the design, I'll just say the top 10 bits is used for the first table. The other 10 bits used for the second table. It's as simple as that. I use the top 10 bits to check which row am I looking in the first table. And the next 10 bits to say which row am I looking in the second table. Is it clear?
After that part of the view access.
Page offset, yes.
So we get a little bit of the remap.
Yes. You know already the physical address, the last 12 bits will be in the physical address. That's come from the real address. All right. So now I just draw that example. I have the virtual address at the top is 32-bit long. The first 12 bits, they are the page offset, followed by the level 2 index bit, followed by the level 1 index bit. Basically, the topmost bit is used to search level 1 table. Level 1 table will tell you where is level 2 table. Then you use the next 10 bits to tell what row in the level 2 table that you want to search, which will give you the physical page. Okay. If you read the textbook that are a little bit more direct in terms of naming, in a 32-bit era, like back in the day, we call the top bits the page directory, and we call the next set of bits the page table, because the directory points to the table and the table points to the page, and just how they name it. All right. But with 4 level, which we use nowadays, it makes more sense at level 1, 2, 3, and 4. Okay, that's why I stick with level 1 and level 2, because you're in 2023, not in 2000, right? If you are in year 2000, that matters. All right, so the first level you can have is 10 bits, right? Which means you can span 1024 rows, 2 to the 10. Your table will have 1024 rows, start from row 0 to row 1023. Depending on the level 1 bit. For example, let's say the level 1 bit is 0, 0, 0, 0. That's 4, right? Number 4. Oops, wrong. Forgot my example. All right, sorry, let me clean it up. All right. 0, 1, 1. Okay, that's number 3. That's number 3. What happened is I will just look at the PTE3. Whatever goes in here, tell me the location of the next table. So this guy will point to here. Now I would then look at the next 10 bit. I'll look at the next 10 bit. All right. And let's say the next 10 bit is, if I remember correctly from this, 100, that's number 4. So you then go to PTE4. You take this part, take that part, you plug in the page offset, and you're done. This is your physical address.
So in this case, only the first section gets changed to the physical address.
Yes, because the other one was a permission bit, right? So the rest are like, can I access them? If I want to manage them, should I keep this page or should I kick them to the memory? Should I kick them to the disk and things like that? All right, any questions so far? Okay. If you know this, I think you should be able to ask the virtual memory part of the exam. Okay, so keep this in mind. Now we'll do a quick break before we go and cover the 4 level, which basically follow same logic. And then now we'll address the problem about the performance overhead, because every time you go through that table is DRAM access. Not nice, right? Not nice. So what do we do? All right, so let's do a quick 10 minutes break. We'll come back at 1:20 and continue. Okay, so any additional questions about the 2-level design? Okay, let's proceed on to it. Now in the 64-bit machine, you would have the offset bit looks the same thing, but it's 4 kilobyte page, right? Then for each level, instead of 1024 entry, you're gonna have 512 entry, so you need 9 bits per level.
Is the offset always 10 bits?
Huh?
The offset always 10 bits? Or is it for the exam?
It's basically the log 2 of the page size. So in your computer, for most OS, if not all, to be honest, it uses 4 kilobyte as the base. That's why it's always stick with the last 12 bits. All right. In the CPU, there's this thing called CR3. It's a special register that points to the first table. Basically, the only thing it does is store where is that first table. Then you use the top bits, top 9 bits, to go into what row am I accessing. Then you go into what row am I accessing for the next table, and so on and so forth. Now in the level 2, that's where permission bits start to come in. So you have the location of the next level. We call this physical frame number. The physical frame number will tell you where's the next table. Then you can store some more additional permission bits. used to manage the page and manage permission. The level 1 table, again, the same, right? You have the physical page number, which is now span the 4 kilobyte range, and then again the permission bit at the end. Then you put the page offset, which is this guy. Plug it in here because I don't need permission bit. For the physical address, it's just the physical page number plugged by the page offset. All right. For the Linux system, when I want to combine a bunch of pages into 2 megabyte page, then the offset would span these two range, and you put it here in the second level. That's why we call this a physical frame number, because that's a page frame. That's 2 megabyte range. The same logic applies, just you go 3 level. The last level tell you where is the page, which is a 2 megabyte rather than a 4 kilobytes. All right.
So
Yeah.
Is unused as index one.
Oh, unused literally is not being used.
What's the purpose for it?
Well, we have 64 bits and we only need how many bits? It's just it's empty. So for example, I had a paper that say, hey, that's unused, so let me use it for some other purposes. So these are basically spare things that you can use from the system. For example, the virtual address you see is only 48 bits, right? 0 to 47. This part is also unused, like the 48 up to 63rd bit. In reality, like people use it for different purposes as well. We can kind of tap additional information to the page or to the physical address to, for example, prioritize certain things, notify that this is like a special page that do X and Y and Z. A quick credit to Ajahn Piti. I think it was a year and a half ago. He was developing some code, and protection bit kicks in. Basically, there was a bug, I think, in the maybe the driver that caused the like you go through the page table and the permission bit doesn't match, so it crashed the program. Right? This is a good thing, to be honest, because if it doesn't crash the program, it means you're trying to have illegal access, essentially. Right? So this is actually a live thing. Now here is the performance issue. All right. The page table, those are in DRAM. Our caching structure, right? Remember this. Access to DRAM takes a long time. Okay, not good. What can we do? The page table structure is used to get the physical address, which means that if I want to access DRAM, right? Let's say you're using 64-bit machine right now on your CPU. Means you have 4 levels. The first problem is I can't even get to my data unless I go to DRAM 4 more times. All right, 4 more times. Then I have the data in DRAM, which means the 5th access is a lot of DRAM accesses. Second issue, your cache. What's the cache for? To make sure your data access is fast, right? But the problem is there are parts of the cache that need physical address, which means that you can't even go to the cache unless you have the physical address. It means that, well, if you will, cache become useless because I have to go to DRAM 4 times already. What's the point of saving the last access? All right, so how do we address both of them? The first one, now let's talk about the solution for the first one. We learned caching. What's the cache for? Make data access to DRAM faster. So can we cache virtual page? So I have a separate cache, right? And I look up, do I have this page? Do I have this page? Do I have this page? And skip all the level. From the virtual address, you go all the way to the physical address. We call this the translation leukocyte buffer, or the TLB. This is a really, really important structure in your CPU because it caches the physical page, essentially. So you have the virtual address, right? The lower part is the page offset, and then the rest we call the whole thing the virtual page number. What you have to do is basically cache the virtual page number as the tag. That becomes the tag, and you use it to search the TLB. You use it to search the TLB. If I have the tag, it means I know what? Physical page. All right. I use the virtual page number as the tag, and I search the TLB structure. If I can find my tag, it means the TLB has my physical page number. If I have the physical page number directly, I don't even have to go to DRAM even once. I just go to the TLB and I'm done. Okay, that takes care of any issue.
Which hardware does?
It's in your CPU. It's actually in your CPU. When you buy a CPU, TLB comes with it. Modern CPU have two levels of the TLB, like when you have multiple levels of the cache, the smaller TLB, which is really quick, and then the level 2 TLB. Now, I said virtual page number per one TLB entry, right? Now you can see the benefit of a bigger page size, right? Because a bigger page size means one entry in a TLB cover bigger range, right? In the 4 kilobyte page, one entry in a TLB is 4 kilobytes because it's one page. Now let's say I have 2 megabyte page. One TLB entry span 2 megabytes. So I am much more likely to find the translation in a TLB. That's why actually that's the main benefit of using a much bigger page. But again, in modern system, you're gonna have fragmentation everywhere. All right. So that's a trade-off. You need to know what program are you using. Many programs actually discourage you from using huge page because you're gonna end up with fragmentation. Where?
Like,
Huh?
does the OS provide like a option for defragmenting the hardware?
Yes, but defragmentation basically means you're moving things around. Moving things around involves you go to DRAM, take that, move it here. It takes a long time. So it's not ideal to do this defragmentation often. But yes, they do exist. And yes, it kicks in once in a while. So if the translation data is not in a TLB, that's when you have to do the page walk and that's it, right? In most modern systems, your TLB hit rate is usually more than 95%, which is a good thing. Only 5% of the time or less, actually much less in the typical sense, you have to go do the page walk, which is should be enough, right? Now, any questions so far about the TLB?
Notice the 5% difference.
Yes and no. Most of the time I would say no because there are also many other performance bottlenecks that would slow down your program that the 5% it does matter, but not a lot. Now, again, the TLB structure, again, store the VPN as a tag. You search the structure, it will give you the physical page number, and you just plug in the page offset. You have everything in the CPU. You don't even have to go to DRAM if your data is in the TLB. All right. Any question? Now, first problem gone, right? Second problem, you need physical address to access the cache. So will the TLB help? It also fixed the second problem. All right. Any questions so far? That's why the TLB is so important. But let me talk about one last concept, right? One last concept. Awesome, I'm making really good progress on time. It's 20 minutes. This one last concept will usually confuse the student because you'll be like, what's going on? Here, the cache has two parts, the tag and the index. All right. This is going back to caching lecture. You have the tag and you have the index. What information between the tag and the index? Which one do you use to tell is that your data? The tag. The tag. So here's my question. I have the tag and the index. Both of them can come from either the virtual address or the physical address, but well, you can pick. In reality, you cannot really pick, but well, you have a choice, right? These are all the 4 choices. I can use physical address for the index or the tag and or. I can also use the physical address for both the index and the tag. The problem here is because virtual address are virtual address. Let's say you launch the same program twice. They're running, the two processes are running, but it's from the same program. They might share the same virtual address, but it's from two different processes. It means that I can have the same virtual address that belong to two different physical address. Because it's two different processes, so they have to have different physical address, right? But it comes from the same virtual address. So the problem is I can have VA1 map to PA1 and the same different process. So this is process 1, process 2. It just happened that virtual address happened to be the same. Which one works here? Can I use virtual address for the index? Does it matter? It doesn't matter. I can use physical address, I can use virtual address, both are fine. But for the tag, which basically tells is that your data? For this particular problem, do I need to use the physical address or the virtual address to tell the differences? You need physical because that's the only thing that tells me the difference, right? So it means that I need the physical address for the tag. Okay, that's why TLB is super important because you need the physical address here. But if you look at it the other way around, virtual address is faster. You have it right away in the CPU. You don't even have to go through the TLB, right? So you kind of want to maximize the chance you can use the virtual address, except only when it's necessary, which is when you have the tag. So definitely, physical address need to be used as a tag, all right? Because we have the homonym problem. Two programs can have the same virtual address by chance, and we need to tell them apart. We need to separate the two physical address. So the tag need to be able to tell the difference. So when you have this question, right, this is not possible. I cannot use virtual address as the tag. So now you have only two options left. Virtually index, which means I use virtual address for the index bit. Physically tag, I use physical address for the tag, or physically index, physically tag. Now, issue with using physical address for both of them is this. The first thing you need to do, if you use physical address for the index, the first thing you have to do, go through the TLB, right? So you have virtual address. The first thing you go is TLB. What's my physical address? Now I have physical address. You use the index to get the set. Then check the tag. All right. The first thing you have to do is I need to go to the TLB to get the physical address in order to get the set ID because the index bit is in the physical address. Before I can go to the cache and get, hey, that's my set 7, for example, I take that and check the tag. Let's say this take 1 nanosecond, 1 nanosecond, 1 nanosecond. So how long is this process? 3, right? Now let's look at the alternative design. I have the virtual address. I use virtual address for the index bit, which is okay. I mean, I just go to the set. It can collide and it doesn't matter. All right. Virtual address, go get this set. And at the same time, I try to also get the physical address from the TLB, right? Because they use the same information, I just forward them to both locations. Then once I have the set, the TLB will give me the tag, right? So I compare the tag. Then you're done. You have the physical address. Again, the same process. This thing takes 1 nanosecond. This thing takes 1 nanosecond. This thing takes 1 nanosecond. How long does the whole process take?
2, so they're simultaneous.
Yeah, 2 nanoseconds. How much faster is this? Yeah, 1 nanosecond faster. You get quite a bit of speed up, right? 33%. Suddenly everything is like 30% faster. Imagine you buy a new CPU and everything's 30% faster. It's magical, right? So even though, so many students ask me like, is that really beneficial? The thing is, the base is really fast already, but you are now much faster compared to the baseline. So that's why we call this as an issue with PIPT. You want to use the virtual address for the index because you can overlap the time it takes to get the set with the time it takes to search the TLB, right? So the benefit is you overlap the lookup of the TLB and you get a much faster process. This is the benefit of, sometimes we call this VIPT because it's quite wordy, virtually indexed physically tagged. Yes. Yeah.
So the set happened in the cache.
Yes, the set is in the cache. But in order to compare the tag, you first need to go and find where's my set and take it and compare the tag, right? So we can use the virtual address for that process. It kind of makes sure if you can save time, do things in parallel, do it. Any question? A quick thing, if you have a TLB miss, you're screwed. TLB is way more important. Well, not to be honest, both of them are important, but the TLB is really important. Because if you miss in the TLB, 5x, like 4D RAM access to get to the physical address.
The way to make it so if TLB misses, you change the style. Like physically done. Physically done.
Well, by that point, it doesn't matter, right? But what happened in a TLB miss? Your modern CPU, this is a little bit out of the scope of your class, right? But in your CPU, there's another caching structure called the page walk cache. So the TLB, right? This is a TLB. This allows you to go from virtual address, skip all level, go to the physical address. It basically allows you to skip every level. So for the page walk cache, you start from virtual address, you skip a few level. So you might skip one level, 2 level or 3 level. You go to like level 4, for example. Then physical address, or you can go from virtual address, go down to level 3. Then you do level 4, then physical address. This is way better than the full process, right? So your CPU has both of them to make sure that you have to minimize the number of page walk and DRAM access they have to.
What is the rate though in TLB? How does the transition?
So you have the virtual page number from your virtual address, right? And then with that, you look up the TLB, you get the physical page number. Once you have the physical page number, you just plug in the page offset and you're done. All right. You can do it now actually. So now you cover caching and virtual memory. When you write a program, let's say you have a pointer. Let's see what happened. Let's say you have a pointer access, all right? Let's see what happened inside the computer. You have the caching structure. This is what you learned in the caching lecture. And you have what we learned today, which is a translation structure, the TLB and the memory management unit that perform page walk. Let's say your data is right here. And you have some pointer in your program, all right? You want to access the data given the address. What happened? So I have a virtual address. The first thing I do, I take the index bit from the virtual address to get the set in the cache. This is VIPT, all right? This is VIPT in play. At the same time, these are, again, virtual address, right? This is virtual address. So I would use the virtual address to check the TLB by extracting the virtual page number. If this is a hit, what happened? If it's a hit, I have the physical address. Yay, I'm done. I go to the cache. Now I look up, is it in L1? If it's in L1, I return the data back to the CPU, right? And then the whole thing is done. If I miss in a TLB, now here comes the problem. I miss in the TLB, MMU takes over, it starts going through the page walk level. In your CPU, for access. The reason why it's a big red arrow is that these are long process. You take a lot of time to go access the page table. Now you finally have the physical address. With the physical address, then you can check the L1. If it's an L1, you go back to the CPU, return the data. Otherwise, you go check the L2 cache. Modern CPU typically these days has 3 levels of caching. So you go to the last level of cache, which is L3. In a big data center, you also have the L4. All right. So it depends on the design, machine design. Some machine have way more level. So if it's missed, you go to the next level. If it's missed again, you can use the physical address to go to your DRAM to access your data, and that's it. That's it.
It's not at the 0.
Then you go to the disk. Then if it's not in DRAM, the OS will start another thread that performs the page fault, which basically we call this a hard fault. Hard fault means that the data is all the way in the disk. The data is all the way in the disk, and I have to retrieve the data from the disk. All right. Any questions so far?
How does it miss in the L1?
How does it miss in the L1 cache? Well, L1 is full. I don't have the data. I check the tag, and the tag is not there. Right? It means I have to check the next level.
Load and then SQL for?
Last level cache. My bad. It's basically last level cache is L3. Some machine will have L3 and L4. Some machine, older machine will have L1 and L2, and that's it. Right? Yeah. That's a wrap of the last module. This one slide is a wrap for the whole thing. Caching, translation. All right. Next week we'll come back and since we somehow we managed to cover the whole thing for the virtual memory, which is an impressive thing. Next week we'll go through the sample exam that we have in T1 2022. But I do encourage everyone to work on it first, because once you go through that, you know what question to ask me. All right. Then on Thursday, probably some review session, and I'll kind of prime you over once you're done with this class. What is PCSA? The next class that you might have heard about. Someone's laughing, which is a good thing. Well, that class you implement a lot of low-level things, so the lab is
Is there a requirement
this
for
class.
only this class?
Yeah. Basically, once you know C, you can start implementing some of the OS things that you use. And if you want to go to a system track or like hardware design track, this is like the path. All right. The class talks about system, which is OS, OS network and architecture in one semester. All of them are just intro material to make sure you know enough about system, network, and architecture that you can basically become like a full-fledged programmer that knows the hardware enough. All right. So that's it for the class today. I didn't realize it's Thursday. Sorry. It's like enjoy your weekend.